So we're going to be working on the first learning objective of the second term of NGSS Physics. And this learning objective is 5-1, identify numerical and graphical patterns to support the claim that electric force is directly proportional to charge and inversely proportional to the square of distance. There's a lot of things in that sentence that I want us to focus on. So first of all, we're looking at a relationship between electric force, which is a new thing we've never talked about before, and two other variables. One is charge, and the other is distance. The relationship between electric force and charge is that it is directly proportional, and that's something we're used to. So you probably already know what it means that electric force and charge are directly proportional. However, when we're looking at the relationship between electric force and distance, it says that it is inversely proportional to the square of distance. Now, inversely proportional is something we've already heard, and it's something you should know what it means. When we say electric force is inversely proportional to distance, you should have an idea of what that entails. However, this is inversely proportional to the square of distance. And while you might have a guess what that means, you probably don't fully understand it yet. So by the end, we need to understand those two relationships. All right, so one of the first things that you'll do in this unit is you'll look at something called the ice sheet interactive, where you're just kind of playing around with balancing the forces exerted on an object by changing the charged particles. So when we're talking about charged particles, we're talking about things like this. This positively charged particle would represent a proton, and this negatively charged particle would represent an electron. Now, excuse me, when we're looking at this interactive and when we're talking about charges in the future, the basic rule that we need to understand is that opposite charges are going to attract. I'm going to use the color green for any attraction in this unit. So opposites attract. I'm going to draw the force. There's going to be a force on the proton this way and a force on the electron that way. And I'm actually going to write attraction over this example. All right. On the other hand, like charges repel, and I'm going to use the color red to show repulsion. So these two protons, they're both positively charged. They're going to experience forces away from each other. They're going to experience a repulsion. On the other hand, these negative electrons are also going to experience repulsion. They're also going to repel because they are also the same charge. Okay, so this is the fundamental rule of this unit. Opposites attract, like charges repel. If we start to change the charges, we start to see relationships between the strengths of those forces. And it's the strength of those forces and those relationships that we're really concerned about. So in this situation, we've got a proton and electron. They are going to attract. So I'm going to draw a force on each one in green, pulling them together. And we're going to label that as FEL. That is the electrostatic force on these two objects. And we're going to totally make up this number. It's not accurate, but we're just going to say that the force of attraction is 1 Newton when those two objects are 4 meters apart. Over here, we have a different situation. We now have twice as many protons and twice as many electrons. And so we now need to think about what is the force going to be when we've doubled the amount of charge. Over here, it was a force of 1 Newton. And just so we're clear, that 1 Newton refers to the strength of this force and the strength of that force. They're both 1 Newton. According to Newton's third law, these two forces are parts of a force pair, where the proton is pulling on the electron and the electron is pulling on the proton, and therefore those two forces have to be equal. Now, this situation is really just the previous situation twice. This proton is pulling on this electron. This proton is pulling on this electron. So if we have twice as much charge, it's reasonable to expect that you would have twice as much force. All right? And that is the directly proportional relationship we were talking about just a moment ago. So if we fill this out, we'll say that doubling the charge will double, and when we say double, we mean times 2, right? Just mathematically, the electromagnetic force. And then it says electromagnetic force and charge have a directly proportional relationship. Okay? Now, looking at the distance between the charges, we also see a difference. And if you remember doing the ice sheet interactive, or if you haven't done the ice sheet interactive, when you get to it, you'll notice that it's not nearly as simple as adding more charge. When you start changing the distance, there's something a lot more complicated that's going on. But just on a basic level, we again have this proton and this electron 4 meters apart. And so the electrostatic force is going to be 1 Newton. Again, if we go over here and we double the distance, so we now have 4 centimeters and 4 centimeters for a total of obviously 8 centimeters. Same proton, same electron. We're now going to have much smaller forces because they're farther apart. They're not going to attract each other as strongly. I'm going to make these forces really small just to drive the point home. And one of the things you'll notice about static electricity is it's very strong when objects are together. If you have a sock or something like that that is really staticky, it can cling very strongly to other things when they're actually right next to each other or almost touching. But if that sock is even a few inches away from something else, the force almost completely seems to disappear. And so what is actually going to happen here is we're going to go from 1/4, and we're not going to double the force. We're not going to halve the force. We're going to quarter the force. Let me change my thickness of my pen. Now, where did that quartering come from? Well, we said at the beginning in the learning objective that distance and force have a relationship that is inverse to the square. And so what we're going to do is we're going to take an inverse relationship. So instead of times 2, okay, we're going to do times 1/2. When we double the distance, we get times 1/2 the force. That would be an inverse relationship. But this is not just an inverse relationship. This is an inverse relationship to the square. And so I'm actually also going to square that 1/2. And so what we really get is when we double the distance, we get times 1/2 squared the force. So we could do that, or we could just do 1/4 because 2 squared is 4. Okay? So this is why we say that electromagnetic force and distance have an inverse square relationship. Okay, let's do some quick math real quick. Just Let's do some quick math real quick, just to make sure we understand what's going on. So let's say we've got our distance here, and let's say we've got our electrostatic force here. So at a distance of 4 meters, we had a force of 1 Newton. Now, if we double the distance, we are going to quarter the force, okay? What would happen if we tripled the distance? Well, we would do the inverse, so it would be 1 over 3, and then we would square it. 1 over 3 squared is 1/9 the force. What if we quadrupled the distance? Well, we would get 1/16 the force, and so on and so forth. All of this is summed up in something called Coulomb's law. Coulomb's law is an equation used to predict the force between two objects that are interacting via an electromagnetic field. Here's a picture of an electromagnetic field. You can't actually see electromagnetic fields, but this is how we sort of draw them to represent what's going on. This electromagnetic field between a proton and an electron represents an attraction. And you can see that the electromagnetic field is basically curving toward the two particles. Over here you see an electromagnetic field between two protons, and that represents a repulsion. And you can see that the lines kind of curve away from each other in this case. Also, you can see from this diagram why it's an inverse square relationship. So as you move away from the particle, you can see that the lines get further and further apart. So that distance indicates the strength of the electromagnetic field. As those arrows get as these start close and then get farther and farther and farther apart, the field is actually getting weaker. And because this is a three-dimensional object, it's getting weaker as this actually spreads out in multiple dimensions. And so the amount of weakness as you move outward decreases by the square of the distance. So that's why we get like 1/4 the force at 8 times the distance, because the field is actually spread out over not twice as much area. The field is spread out over 4 times as much area. All right, so here's the equation for Coulomb's law. And this equation, we're just going to color it in first. It starts with FEL right here, which is the value of electrostatic force. And then it has this negative K value. The K stands for Coulomb's constant, which right here is 9 times 10 to the 9th. It's just a really, really huge number that never changes. It's always the same in this equation. The reason it's such a huge, big number, or the significance of that, is that this is a really strong force. Very small amounts of charge create really strong pull. That sock that we were talking about that might be sticking to some clothes in the dryer, it might only have a few, like a handful of electrons and protons extra on it that are creating that charge, but that very small amount of charge imbalance creates a really huge force. Gravity, on the other hand, has a similar equation because gravity is also an inverse square relationship. But the constant in gravity is ridiculously small because unlike electrostatic forces, gravity is very, very, very weak. And I know it controls a lot of our lives, but think about it. In order to feel the amount of gravity we do, we have to have an Earth that's enormously massive in order to generate that gravity. Whereas a tiny little sock with just a handful of extra electrons or protons can create a significant amount of static electric force that can actually be strong enough that that force attracts the sock to something more powerfully than gravity is pulling the sock down to the earth. So just keep that in mind. Electrostatic forces are actually dramatically stronger than gravitational forces, and really most forces. All right, Q1 in this equation, which is just sort of a light green here, that represents the first charge, and that is measured in coulombs of charge, just so you know, a capital C. Q2 is the charge of the second object, also measured in coulombs, and R down here is the distance between the objects measured in meters. And notice, this is really, really, really important. I'm going to keep saying it, that R is squared. Okay, when we're doing a calculation in Coulomb's law, any positive value in that equation is going to represent attraction. And any negative value in that equation is going to represent repulsion. But to be honest, even though I have some examples down here, you can see that these two objects, this had a charge of -1, this had a charge of +1, and the distance between them was 1 meter squared. Here's our Coulomb's constant. So when you do all that math, you're going to get the answer for the electrostatic force right there, and that's going to be positive. In this other example, you're going to do the exact same thing, except you have two positive charges this time. Same distance, same Coulomb's constant, because it's a constant. And what that's going to do is it's going to give you a negative charge, or a negative value for the force. And so the positive value over here on the left tells you that they're going to attract. This negative value tells you they're going to repel. But honestly, I would just use the opposites attract rule. If you're trying to figure out if they're going to attract or repel, just, you know that these are opposites and they're going to attract. You know these are like charges and they're going to repel. And then once you use that rule, you can kind of just ignore the positive or the negative sign on the front. Doesn't really mean much. Okay. Last thing we're going to talk about, we're going to look at graphs of the relationships just to sum this up. So here I have the relationship between electrostatic force and charge. And remember, this is a direct relationship. So as we add more charge, we get more force. It's linear. Double the charge gives you double the force. Over here, distance and electrostatic force have an inverse relationship. So more distance gives you less force, but it's not linear. It's got this very dramatic curve, and again, that's because this is an inverse square relationship. Now, what that means, and what I want to highlight, is that if you look at this section of the graph right here, you can see that when the objects are close, really zoom in here, the forces become extremely large. Okay, whereas over here, you can see this big dip, and then you get to this spot over here. Over here, when the objects are far apart, the forces very quickly drop off to almost nothing. But notice that it actually never becomes zero. Charged objects anywhere in the universe technically have some force on each other, which is kind of weird. But the force dramatically drops off, never entirely reaching zero. All right. I know those were really long notes, but that's what you need to know about Coulomb's law.